Welcome! In this video, I'll show you how to solve problem 7.1 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, this problem asks us to use the Gaussian trial function to obtain the lowest upper bound you can on the ground state energy of two different potentials. On part A, we have the potential that is simply alpha times the absolute value of x, and part B is alpha, which is of course some constant, times x to the fourth power. So that's what we have to do. And of course, the Gaussian trial function is the same that we have been using so far. So just as a reminder, it's some constant times e to the minus bx squared, where b is the parameter that we will have to minimize later on when we find the energy. All right. Once again, as a quick reminder, just in case you have forgotten or are unsure, what the variational principle tells us, right, is that we can always find an estimate, right? If we don't want or if we can't solve the Schrödinger equation for a particular potential, what we can do is that we can take some trial function like this psi, and we can find the expectation value of our Hamiltonian in these states. And this value that we will get will always at least overestimate the value for the ground state of the energy that we are actually looking for, right? So we'll always get a value that is either the same or greater than what we're looking for. We don't really know how far off we are, but if we take a relatively good guess, then we can get a relatively good result. Okay, so that was just a summary. Now let's go for part A. And actually both of them will have a somewhat of a similar, at least they will have a part in common, because the Hamiltonian, in both cases, of course, will have the kinetic term, right? Minus h bar over 2m d squared dx squared. And then we have the potential part, which in case A is alpha times the expectation value of x. So it will be, of course, convenient to calculate the kinetic part, which we'll call t, and this is, of course, v. It will be convenient to calculate it by itself so that we can then just plug the value in. If you have been watching this series, you have already encountered this. You should already know the value. You don't have to know it by heart, but you already might know the value. I'm going to calculate it anyways. So if you have already seen how this is, just skip ahead. I'll always put the timestamps on the video. All right. So let's begin calculating this expectation value. So the expectation value of the Hamiltonian will, of course, be the expectation value of each one of the individual parts. So the kinetic and the potential parts. Now let's begin with the kinetic, right? Again, I'm going to separate them mainly for convenience. You could, of course, do it all together, but it's going to be more work. Plus, doing it separately allows me to reuse the result since it's going to be popping up quite often. Okay, so the expectation value of the kinetic term is going to be the integral from minus infinity to infinity of our wave function, which is a to the e minus bx squared, and then we get minus h bar squared over 2m d squared dx squared acting on the wave function, right? Which is going to be a e to the minus b x squared dx. So let's calculate this derivative. So let's derive the wave function twice. So the first derivative is going to be, well, let's leave the a outside, right? Let's just put it here since it's a constant. It doesn't matter. There's no need to be carrying it out around all the time. So the first derivative will simply be minus 2bx times the exponential, right? Because of the chain rule, don't forget about it. The derivative of the exponential would be minus b, and then you have to derive with respect to the derivative of x squared, right? It's the derivative of the function times the derivative of what is inside the function. So don't forget about that x, it's extremely important. Now we have to derive again. So d squared dx squared. So here we have to apply the product rule. So first deriving the x, we get minus 2b e to the minus bx squared. And then deriving again the exponential, we get the same thing. So this part will get squared. So it will be plus for b squared x squared e to the minus bx squared. Okay, so let's plug it all into our kinetic term. So this will be, actually let's leave some room for our constants outside. So we can pull out the a square, the minus h bar squared over 2m. And from this part, we can pull out b and 2. And we can actually even pull out a minus sign, but we'll have to change this. So we can do it like this. And then this minus sign will go away. So we still need 2. Okay. We get minus infinity to infinity. And then, of course, the exponentials multiply. So we get e to the minus 2bx squared. And this will now multiply all that is in here. So this is simply a 1 now because we already considered the exponential and we factored out the 2b. So the first part is simply this exponential. And the second one will now be minus. And here we still have 2b and then x squared e to the minus 2bx squared. Okay, so we have two integrals that we have to solve. Now, how do we solve this exponential? Well, this exponential is extremely important that you know. I've mentioned in the previous videos, starting with the first one, which we might as well just label I1. So I1, this is what we call a Gaussian integral. It goes from minus infinity to infinity, e to the minus 2bx squared dx. Gaussian integrals are integrals of the form minus infinity to infinity of e to the minus something x squared. And in that case, the result, you cannot use like manual integration. You have to use some sort of numerical method. So I recommend that you learn this, by memory. It's not particularly hard. It's simply square root of pi divided by whatever is accompanying the minus x squared. So in this case, 2b. Don't make the mistake of putting the minus sign in here. Okay, so that's the result from the first integral. So maybe let's plug it in right away. All right, so square root of pi over 2b. Okay, and of course, let's not forget to put the integral sign here. All right, now the other integral. Now this we will just label I2. So let's, of course, leave the constants just outside. So maybe let's write it as minus 2b times the integral. There's really not much point in keeping the constants in. So our integral is minus infinity to infinity of x squared e to the minus 2b x squared dx. So this has this part that is kind of Gaussian, but it also has this annoying x squared. So there are a few ways to integrate this. My way to do it is a way that I feel is really, really easy. I mean, it is a trick, so you have to learn it. But once you learn it, it's extremely, extremely powerful. You're going to see, in fact, that we used it a lot in this video and in other videos to come. So how do we derive this? Sorry, integrate this? Well, you have to see that this x squared is also up here. So if we had some e to the minus, let's call it beta x squared, and we were to take the derivative with respect to this parameter beta, then what do we get? We get minus x squared e to the minus beta x squared, which is kind of exactly what we have here, except for the minus sign. So that is the trick that we will do. So we will multiply here both sides by a minus, so we get the minus here. So now we can replace the x squared e to the minus. Instead of beta, we get 2b, of course, but for now, let's stick to the beta, x squared. And we can replace it by this other thing. And what happens? Now we get integral from minus infinity to infinity of, well, let's put the minus sign down outside, derivative with respect to beta, e to the minus beta x squared dx. And we can pull the derivative outside, right? This integral is only with respect to x. It doesn't affect beta, so we can just pull it outside. There's nothing wrong with that. And we are left with a Gaussian integral. Right? And we know how to solve it. We literally just saw it. So that's going to be minus the derivative with respect to beta of square root of pi over beta, right? The thing that accompanies the minus x squared. So now to conclude, we only have to take the derivative. So derivative with respect to beta of beta to the minus 1/2, right? That's minus 1/2 beta to the minus 3/2, right? I simply took the derivative of beta to the minus 1/2, which is what we had here. And now let's simplify this. Let's plug in the value of beta, which is 2b. So square root of pi, the minus signs cancel out, divided by 2, and then times 2b to the minus 3/2. Okay, so that's the result. And we can now just go ahead and plug it up here. So we get square root of pi over 2 times 2b to the minus 3/2 power. But we already have a 2b here, so we can multiply these, and we get, instead of minus 3/2, we get minus 1/2, right? So let's now get rid of all this. We don't need it anymore. Bye-bye. Okay. So now there's a few things we can see. Maybe let's rewrite this thing right here. So we can simplify a little bit. So we get a squared h bar squared b, the 2 cancel out, m. We can actually factor out, actually now let's go step by step. I don't want to confuse anybody. So square root of 2b, then we get minus square root of pi, and this 2b right here is also in a square root, right? It's minus 1/2, so we can write it as square root of 2b also. And we also have 1/2. So as you can see, we can easily factor out the square root of pi over 2b. So we get a squared h bar squared b over m. Didn't factor it. So we want to factor out square root of pi over 2b. And we get 1 minus 1/2, which is, of course, 1/2. So here we get a squared h bar squared b over m square root of pi over 2b times 1/2. So maybe let's put the 2 here. Okay, now there's still something that we have to do, because this a is the normalization constant for our wave function. So let's normalize the wave function so that we can find the value of a squared. So to normalize it, we said 1 has to be equal to the integral from minus infinity to infinity of our wave function squared, right? Minus bx squared. The modulus squared, but it's real, so it's the same in this case. So minus 2bx squared dx. We can put the a squared outside, and this is again a Gaussian integral. So we get square root of pi over 2b. So here we can easily solve for a squared, right? We divide by this, so we get square root of 2b over pi. So let's plug it in here. So we get square root of 2b over pi, which is a, times everything else. So h squared b 2m square root of pi over 2b. So as we can see, this whole thing, right, they just cancel each other out. So we get that the expectation value for the kinetic term is h bar squared times b over 2m. It of course depends on b. We'll have to find the value of b that minimizes the total energy. Okay, so that is the kinetic part. I'm gonna select it and keep it somewhere safe, because we will surely need it again. Okay, so maybe, I don't know, here or something. Okay, now let's get rid of this. And let's begin working with the potential. So now we have to do exactly the same procedure, except that, wait, why is it? Okay, there we go. Except that our potential is now this alpha x. Okay, so this is actually where the a part really begins. The rest was kind of an introduction. So the expectation value of the potential is going to be integral from minus infinity to infinity of the wave function. So we get a e to the minus bx squared. And now comes the potential, a times expectation value of x. And then again, e to the ae minus bx squared. All right, so we can take our constants outside. So we get a squared alpha. We, of course, already know the value of a, right? Just as a reminder, the a squared is square root of 2b over pi. We just found that by normalizing. Then what else do we have? We have still the integral, and we have the absolute value of x e to the minus 2b x squared dx. Okay. So now we have to solve this integral. Well, how do we solve it? That is the question, and whenever you face something like this, ask yourself, well, what is the problem? What is the thing that makes me feel lost? And we know this Gaussian part, the problem is the existence of the absolute value. That is the issue, right? So how do we get rid of the absolute value? Now, maybe you should think back to when we have an integral of like just absolute value of x, for example, and how you used to work with that, because we know that the absolute value of x is going to be minus x if x is negative, or just x if x is positive. So basically there's two different cases. And if you think maybe of the graph of the absolute value of x, it is this thing right there, which is an even function, right? That's important to note, because e to the minus 2bx squared is also even, right? So that is one way you could go about it, because the most important thing here is that we have to get rid of this absolute value sign. So there's two ways to go about it. Maybe there's even more, but at least there's two that I can think of right now, which is that one, we say, well, we know this thing is even, so the integral from minus infinity to infinity is going to be the same as 2 times the integral from 0 to infinity of x to the e to the minus 2b x squared dx. And of course, since now we are only in the positive regime, we don't really need the absolute value sign, right? It's the same as simply x. Wait, why isn't Control Z working? Oh, because I'm pressing Control X. Whoops. And from here, we could go ahead. The problem is that now we are dealing with integral from 0 to infinity. This is, of course, perfectly valid, but this is not really the way that I like to solve this problem. It's, as I mentioned, perfectly valid. I just want to show you one of the ways. So this is way number one. I personally like to do it differently. What I like to do is I like to separate the integral. So I say, all right, I know that this square root of x is going to be minus x between minus infinity and 0, right? So I'm going to say, all right, so let's separate this integral from minus infinity to 0, and then I write it as minus x e to the minus 2b x squared. It's going to be exactly the same, right? I guess what I'm doing here is I'm just doing an extra step, but I really think that this is very, very good, like pedagogically, when you're first encountering this sort of integrals. We don't need to put the minus sign in here, of course, because this is already even dx. And then in the second part, we get integral from 0 to infinity. And what do we get then? X e to the minus 2b x squared dx. And now we can apply the rules for integrals. The integral from minus infinity to 0 is the same as minus the integral from 0 to infinity. So here we can just change our endpoints and add a minus sign, which cancels out the minus sign. So in the end, we get 2 times the same thing. And we end up exactly where we were before. But I think that this is sometimes a bit more intuitive. So we basically end up in the same place. I guess that it is indeed the same method, just that with 2 different ways to get to it. Well, either way, once we get to this, well, of course, let's take the 2 outside first. And now, what do we have in here? How would we integrate this? Well, this kind of looks like a Gaussian integral. What I would like to do is try to transform it into a Gaussian integral. So as we saw previously, right, when we derive So we take d dx of e to the minus 2bx squared. What we get is minus 4. Well, I guess when we did it before, it didn't have this 2, but the idea is the same. And minus 4bx e to the minus 2bx squared. So what I mean by this is that when we derive this exponential, we get this thing right here. So we can now rewrite some of this. Maybe I should put this in a box so that we don't get confused here. So d dx e to the minus 2bx squared times minus 1 over 4b is the same as x times e to the minus 2bx squared. So, and that is exactly what we have in here, right? So now let's replace the inside of the integral with what we just wrote down. So this, maybe let's put the minus sign outside, and with 1 over 4b d dx integral of e to the minus 2bx squared dx. And here, fundamental theorem of calculus, we have the integral of the derivative. We are simply going to get our function evaluated at the endpoints. So we get minus 2 alpha a squared divided by 4b. And then what do we have right here? This is going to be e to the minus 2bx squared evaluated between 0 and infinity. So at infinity, this is going to go to e to the minus an extremely large number, so that's going to be 0. And at 0, it's going to be e to the 0 is 1. So we're going to get minus, maybe I'm going to just do it explicitly. So as x goes to infinity, we get e to the minus an extremely large number, kind of, right? Infinity is of course not a number, so it doesn't make sense if you do it like that, but we get e to the minus a very large number, so this goes to 0. And then we get e to the minus 0, which is 0. So we get e to the 0, which is 1. So we get a minus sign in front. So we get 2 alpha a squared divided by 4b. Okay, and of course, let's plug in the value for a squared, which we already know. And let's simplify the 2 with the 4. So we get alpha divided by 2b times square root of this 2b over pi. So if we do this, we get alpha, and then we get square root of 2b pi. Okay, so this is the expectation value of the potential. So now let's put everything together. So there is our value, so h squared b over 2m. So the expectation value of the Hamiltonian, which is of course going to be the energy estimate, this is going to be the value for the kinetic term, which we already found, h bar squared b over 2m, plus the kinetic one, which is alpha square root 2b pi. Okay, so now we want to minimize this. So we want to take the derivative of our energy with respect to b and set it equal to 0. Okay, so let's see. This is going to be h bar squared over 2m plus alpha over square root of 2 pi. I'm just putting the constants in front. And then we derive the b to the minus 1/2, which will be minus 1/2 b to the minus 3/2. Okay, now we have to solve for b, so let's go step by step. We don't want to make a dumb mistake at this point. So on the left-hand side, I'm going to have this. So we get b to the minus 3/2. Actually, maybe it's going to be even better if I do it like this. So 1 over b to the 3/2. It's the same, but just to make sure that I don't make a dumb mistake, times alpha over 2 square root of 2 pi is equal to h bar squared over 2m. So the 2's cancel out. And then to solve for b, I need to multiply through. So I'm going to get b multiplying through, right? Cubed over 2 this is equal to alpha times m divided by h bar squared square root of 2 pi. Did I do this correctly? So multiplied, divided. I think I did. And now we need to take the, basically to the power of 2 over 3. So we get alpha m and h bar squared square root of 2 pi to the 2/3 power. Okay, so this is the value of B that minimizes the energy. So to find the minimum energy, we are going to have to plug this into our formula for the energy. Wait, what's going on here? There we go. Put it to the side. Maybe get rid of this too. So we can just go ahead and plug everything in. Okay. So what is going to be the minimal energy? Let's see. So we get h bar squared to m, and then we just have to plug in B. So we get alpha m h bar squared square root of 2 pi, and all of this to the 2/3 power plus, okay, and let's plug it in here. So we get alpha over square root of 2 pi times 1 over square root of B. So we get alpha m over h bar squared square root of 2 pi, and this thing is to the 2/3 power, but all of it is to the 1/2, right? It's the square root of B. So yes, now we have to, of course, apply the 1/2 to the 2/3 in the exponent. So we get 1/3. So it's going to be to the 1/3 power. And now finally, we need to flip this around. So we're going to get h bar squared square root of 2 pi over alpha m to the 1/3. Okay. Okay, so now it's time to multiply. I mean, in principle, this is already done, but of course, we want to get an answer that is as simple as possible. So let's multiply through, and then let's see if we can find any similarities at all. So we have, okay, so with the h bars, we have h bar squared divided by h bar to the 4/3. So that means that we're going to get 2 minus 4/3 in the exponent, which we can rewrite the 2 as 6 over 3. So we get 2/3. So we're going to be left with 2/3 upstairs, right? Now, the alpha is going to remain the same. So alpha to the 2/3. And then we get m. So we have m to the 1 here, m to the 2/3. So we are going to be left with m to the 1/3 downstairs. Then we have this 2. So we have this 1/2, which is basically 2 to the 1, but downstairs. And here we get 2 to the 1/2. So maybe let's do it like this. So just to see the power, we get 1 plus, and then we have 1/2 times 2/3. So we get 1 plus 1/3, which is 4/3. So we get 2 to the 4/3 power. Let's see, we use the h bars, we use the alpha, we use the m's, we use this, and we still need the pi. So pi is also going to have 1/2 and 2/3. So we get pi to the 1/3 power. Okay, now for this part right here, alpha, we're going to have also 2/3, right? We have 1 minus 1/3. So we get alpha to the 2/3 power. Then we have h bar squared to the 1/3. So we get 2/3. Then we have square root of 2 pi to the 1/3 upstairs. But okay, maybe let's do this on the side as well, just to make sure we get it right. So we have 2 pi to the 1/2. We have 1/2 times 1/3 upstairs. And then we have 1/2 downstairs. We need to subtract 1/2. So basically we can factor out 1/2, and this will be 1/3 minus 1, which is going to be minus 2/3. So we are left with square root of 2 pi to the 2/3 power. Yeah. Okay, and then we have m to the 1/3 downstairs. So we did this, we took this into consideration. This was 1/3, 1, so we get 2/3 downstairs, and m. Okay, so we used everything. Good. So now let's compare both of these expressions and see how we can simplify them further. So both of them have h bar squared, well, h bar to the 2/3 is what I mean. They also have alpha to the 2/3. They also have m to the 1/3. They also have, let's see. So there's a 2 pi to the 2/3 here. And we wrote it a little bit different, right? So I guess we have to now pick, do we want to write it as square root of 2 pi or as pi without the square root? Maybe let's keep it, I guess it doesn't really matter. Maybe let's keep it as square root of 2 pi, no real reason. All right, so if we write it as square root of 2 pi to the 2/3, let's see. Actually, I think it's easier to do it the other way around. So turn this separately. So this would be 2 to the 1/3 and pi to the 1/3. Just double checking. Yes. So this means that we can pull out pi to the 1/3, but then we have 2 to the 1/3 here, and here we have something else. So we could consider this to be this 2 to the 4/3 is the same as 2 to the 1 plus, or well, times, I mean, the exponents will add up, times 2 to the 1/3. We can factor out 2 to the 1/3, but we are left with a 2. So we are left with 1/2 here. And here we are left with nothing else. We used everything. So basically we are left with 3/2 times this entire thing. So h bar 2/3, alpha 2/3, m 1/3, pi 1/3 to 1/3. I guess I could have just written the 1/3 as an exponent. That would have been easy. So we get h bar squared, alpha squared, m pi 2. And all of this to the 1/3. So that is the minimal energy for part A. Okay, so now let's go for part B. So in part B, our Hamiltonian will be the same as before. It will be the same kinetic part, but of course the potential will be different. Now we have alpha times x to the 4th power. So what's up? How do we do this? Well, of course, the expectation value for the Hamiltonian will be, as before, the expectation value of the kinetic part, which we actually already know, right? It's h bar squared b over 2m. It's literally the exact same as before. That's why we don't really have to calculate it again. And then we have alpha x to the 4th power, the expectation value of this with our wave function. So let's calculate that, right? This is the potential. So the expectation value of the potential will be integral from -infinity to infinity of our wave function squared, and then alpha x to the 4th power. So we can, of course, pull all of our constants outside. So alpha, a squared, they can all go outside. And e to the minus 2b x squared, x to the 4th power dx. So what's up here? How do we solve that integral? Well, the answer to that is that this is very, very similar to the trick that we used before, because previously we had a case where we had the integral of x squared e to the minus 2bx squared. And when we applied our little trick, right, with the whole derivative with respect to beta thing, we ended up with e to the minus 2bx squared, right? We got rid of x squared. Every time we applied that trick, we basically got rid of x squared, because every time you derive this exponential with respect to beta, which is this thing right here, in this case 2b, then you get a x squared. Now let me make this even clearer. I'm going to show you. So if we derive this once with respect to beta, so let's call minus 2b just beta, we get minus x squared e to the minus beta x squared. Now let's apply a second derivative with respect to beta. In that case, we get yet another minus x squared, and we are left with exactly the same thing that we have here. Of course, with beta being 2b. So let's plug that in. So our potential, the expectation value of the potential, I actually meant to change color. The expectation value of the potential is going to be alpha a squared integral from minus infinity to infinity. And now instead of this exponential x to the fourth, we are going to get d squared, the beta squared, e to the minus beta x squared, dx, of course. And the beta is 2b, right? Don't forget about it. So we can, of course, now pull this d over d beta squared out of the integral. So, and we already know what that integral is. It's simply a Gaussian integral. That's why we used this trick. And that's going to be square root of pi over beta. So let's now derive with respect to beta. So square root of pi. And what do we get? Well, if we derive once, we are going to get minus 1/2, because this is, of course, beta to the minus 1/2 times beta to the minus 3/2. And now we want to derive again, so let's pull the minus 1/2 out, alpha a squared square root of pi, and then we get minus 3/2 beta to the minus 5/2. So we get 3/4, then alpha a squared square root of pi, and beta to the minus 5/2. Okay, now of course let's rewrite beta. It is 2b, so we get 3/4 alpha a squared square root of pi. Actually, let's plug in the value for a squared as well. So we know a squared is square root of 2b over pi, and then we get square root of pi, and then we have 1 over 2b to the 5/2. Okay, so here we can simplify a few things. Square root of pi cancel out, and we have square root of 2b, which is 2b to the minus 1/2, or sorry, to the 1/2, minus 5/2. So we are left with minus 4/2, which is 2. So basically 3/4 alpha, and then 1 over 2b squared. I'm just double checking that I did this correctly. So 5/2 minus 1/2, and you are left with 4/2, which is 2. Yeah. Okay, so this is our value for the potential. Thus, the expectation value for the Hamiltonian, which is of course our estimate for the energy, is going to be h bar squared b over 2m, which is the kinetic part, plus 3/4 alpha over, I guess we could write this as 16 since there's another 4, 16 times b squared. Okay, so now we want to minimize this energy with respect to b. We want to find the value of b that minimizes the value for the energy. So let's, actually, it's not a value yet. We are deriving with respect to b and setting it equal to 0. So we get h bar squared over 2m from this first part, and then 3 over 16 alpha times, this is b to the minus 2, so we get minus 2 b to the minus 3. Plus, of course. So now let's solve for b. We can add this to the left-hand side, so we get 3 over 8, right? Simplifying this 2 with the 16 alpha times 2b minus 3. So I guess this also cancels out a little bit. It's a 4 now. And this is equal to h bar squared over m. So from here, we now have to multiply by b cubed and get rid of this. So we get 3 alpha m over h squared. This is equal to b cubed. So if we want to find b, we need to get this to the 1/3. Let's double check. So we multiply by b cubed. We have a b cubed here. Multiply by m divided by h bar squared. Oh, I'm missing a 4. That's why we double check. Okay, there we go. And that 4 is because that's 8 and that's 4. Yes, okay, amazing. So now let's plug this into our value for the energy so that we can find the minimum value for said energy. Okay. So in the first part, we get h bar squared to m, and then 3m alpha b is v4 h bar squared to the 1/3 plus 3 over 16 times alpha times 1 over b and squared. So let's flip this around and square it. So we get 4 h bar squared 3 alpha m to the 2/3. Okay, now what else? So just as before, let's multiply through and see, what powers we have. So here we have h bar squared and h bar to the 1/3. So this would be h2 minus 2/3, which is 6/3 minus 2/3. Yeah, so this is h bar to the 4/3, I believe. There's nothing to contest this 3, so, we get 3 to the 1/3, nothing new there. Then we get alpha to the 1/3. And what else? Here we get, well, the 2 can stay outside, so 1/2. And then we have m to the 2/3. And this is, I guess this 4, we can rewrite it. Maybe it's not necessary, but let's see. We can rewrite it as 2 squared. So we get 2 squared to the 1/3. So we get 2 to the 2/3. I don't know if it's going to be necessary, but since there's also 4s and 16s and a lot of powers of 2, maybe it's going to be useful. So let's see. Then we have 3 here. But, well, let's begin with 1 over 16. And then we have 3 to the 1 minus this 2/3. And the exponent, of course, the minus. So we get 3 to the 1/3, alpha to the 1/3. And then we have 4 to the 2/3. Or maybe let's write it as 2 to the 4/3. H bar squared to the 2/3, which is 4/3. And then we have the m to the 2/3. Okay, so there seem to be quite a few things in common. So we have h bar to the 4/3, 3 to the 1/3, alpha to the 1/3, m to the 2/3. But then here we still have a few things. So we still have 1/2 times 1 over 2/3, right? Because I considered this, and this. Yes. And here I used this, and this. So in the second part, we still have 2 to the 4/3 over 2 to the 4, right? Which is the 16. So how could we simplify this? I guess we could begin by maybe, because we have 2 to the 2/3. If we could somehow turn this into a 2 to the 2/3, we could factor it out and just add whatever is left. So here we have 4/3 in the exponent, and we're going to subtract 4, which would be 12 over 3, which is 8 over 3, minus, of course. And we could rewrite this as minus 6 over 3 minus 2/3, which is basically minus 2 minus 2/3. Now, what do I mean by that? This entire thing then, we can rewrite as 1 over 2 squared minus 2 to the, sorry, not minus, multiplying, times 2 to the 2/3. Which is amazing because we can now factor out 2 to the 2/3. So now all we have to do is add these two together, which is 1/2 plus 1/4. So we can take minimum denominator. So we get 2/4. So this is going to be 3/4. So 3/4 times, and this would be h bar to the 4th, 3 alpha m squared, 2 squared, and all of this to the 1/3 power. So this would be the minimum value for the energy. So as you can see, all we did in both of these problems is that we begin, of course, we have to normalize the wave function, but then we just take the expectation value of our Hamiltonian, which will mean expectation value of the kinetic part plus expectation value for the potential, and it's simply doing these kind of annoying integrals, then plugging it in, right, into our value for the energy. It will be in terms of our parameter b. We have to variate that parameter, that's why it's a variational principle. We minimize with respect to it, and then when we find the value for b, we plug it back in. And that's all we do in every single problem. The integrals can be very annoying, but it is arguably quite a lot better than having to actually solve the Schrödinger equation. So I hope this was useful. If it was, please make sure to leave a like on the video, comment, maybe share it with some of your classmates. It would really help me out a lot. So I'll see you in the next video. Thank you very much for watching.